Hello, dear friend. Welcome to another quiet journey through the cosmos. I'm so glad you're here tonight. Some nights the sky feels like a memory you can almost touch. Stars blink softly as if they remember something the universe whispered long ago. And maybe they do. Because right now, at this very moment, something ancient is touching your skin. It's not the wind, it's not starlight from distant suns. It's older than that. Much older. It's a kind of light that has traveled for nearly 14 billion years, crossing the entire history of everything just to reach you tonight. It doesn't burn, it doesn't glow. You can't see it with your eyes. But it's there, always there, like a gentle hum beneath the silence. Scientists call it the cosmic microwave background. But perhaps a better name would be the light that remembers everything. Before we drift deeper into this quiet wonder, I want to pause for just a moment. If you find comfort in these gentle explorations of the universe, you might like to stay a while. You can softly tap the like button, subscribe if you'd like more stories, whispered under starlight, and ring the little bell, not for noise, but so the next quiet night can find you again. Thank you for being here. Now, let's drift. Tonight we're going to rest with the oldest light in existence. We're going to let it tell us its story, not with words but with warmth, with stillness, with the kind of patience only the universe knows how to hold. You don't need to understand everything. You don't need to take notes or remember facts. Just breathe. Just listen. And let the cosmos do what it does best. Remind you that you're a part of something vast, something ancient, something that began long before words had meaning. The cosmic microwave background isn't just light. It's the afterglow of creation itself. Imagine the universe when it was only 380,000 years old, still a baby by cosmic standards. Back then, everything that would ever exist, every star, every planet, every atom in your body, was pressed together in a state so dense, so hot, that light itself couldn't move freely. Photons, the tiny particles of light, were trapped in a thick fog of matter, bouncing endlessly between electrons and protons like children lost in a crowd. The universe was opaque. You couldn't see through it, not even for a moment. It was a place of pure energy, glowing white-hot, shimmering at temperatures around 3,000 degrees Kelvin. That's hotter than the surface of some stars. But then something beautiful happened. The universe kept expanding, kept cooling, kept breathing outward into the dark. And at a certain point, a threshold was crossed. The temperature dropped just enough for protons and electrons to come together to hold each other for the first time, forming simple hydrogen atoms. Scientists call this moment recombination, though it's a strange name because these particles had never been combined before. It was more like a first meeting, a first embrace. And in that instant, light was set free. For the first time in the history of everything, photons could travel without being blocked. The fog lifted. The universe became transparent. And those photons, that ancient light, began a journey that would last until now, until this very second, traveling across the expanding fabric of space, stretching and cooling, until they became the faint microwave glow that surrounds us tonight. This light has seen everything. It was there when the first atoms formed. It witnessed the birth of the first stars, the first galaxies, the slow gathering of matter into clusters and filaments that would one day hold planets like ours. It watched as our own sun ignited as Earth cooled, and oceans formed as life began to stir in shallow waters. It saw dinosaurs rise and fall. It saw humans learn to look up at the sky and wonder. And through all of that, this light kept traveling, kept spreading, kept whispering the same ancient story. I was there when it all began. But here's the part that makes you pause. Here's the part that feels almost like a secret. This light isn't somewhere far away. It's not locked in distant galaxies or hidden behind cosmic veils. It's here, right now, all around you, passing through your body at this very moment. Every second, billions upon billions of these ancient photons stream through the room where you're resting, through your skin, through your bones, carrying with them the memory of the universe's first light. You are quite literally bathed in the echo of creation. You always have been. You always will be. Scientists estimate that the cosmic microwave background fills the entire universe with a temperature of about 2.725 Kelvin. That's just a few degrees above absolute zero, the coldest temperature theoretically possible. It's a whisper of warmth, barely there, but still measurable, still real. If your eyes could see microwave radiation instead of visible light, the night sky wouldn't be black. It would glow softly evenly in every direction, like a gentle ember that never quite goes out. Some researchers describe it as the most perfect blackbody radiation ever observed, meaning it follows the laws of thermodynamics with almost flawless precision. The universe, it seems, knows how to cool down gracefully. And yet, this light isn't perfectly uniform. If you could measure it with extraordinary sensitivity, you'd notice tiny fluctuations, small differences in temperature from one patch of sky to another. These variations are incredibly subtle, only about 1 part in 100,000. But they matter. They matter more than almost anything, because those tiny ripples, those faint imperfections in the ancient light, are the seeds of everything that came after. They mark the places where matter was just a little bit denser, where gravity pulled just a little bit harder, where the first stars would one day ignite. Without those ripples, the universe would have remained smooth, lifeless, empty. But because of them, galaxies formed, planets formed, you formed. Think about that for a moment. The reason you exist, the reason anything exists, is because the early universe wasn't quite perfect. It had wrinkles. It had subtle differences. And those differences grew over billions of years into stars and worlds and minds capable of looking back and seeing where they came from. Some scientists call this the most important discovery in cosmology. Others simply call it beautiful. Both are true. The story of how we found this light is just as remarkable. For most of human history, we didn't know it was there. We looked up at the night sky and saw stars, saw planets, saw the soft glow of the Milky Way, but we had no idea that beneath it all was this deeper light, this quieter song. It wasn't until the mid-20th century that scientists began to predict its existence. Physicists like Ralph Alpher, Robert Herman, and George Gamow theorized that if the universe really began in a hot, dense state, then it should have left behind a kind of thermal afterglow. They calculated that this glow should still be detectable, cooled down by the expansion of space existing now as faint microwave radiation. But for years, their prediction was largely ignored. It seemed too strange, too abstract, too difficult to test. And then, in 1965, something unexpected happened. Two radio astronomers, Arno Penzias and Robert Wilson, were working at Bell Labs in New Jersey, trying to calibrate a large horn-shaped antenna for satellite communications. They kept detecting an annoying hiss, a persistent background noise that wouldn't go away no matter what they did. At first, they thought it was interference from nearby New York City. Then they thought it might be caused by the antenna itself. They even wondered if it was pigeon droppings, because a pair of pigeons had been nesting inside the horn, and perhaps their waste was somehow affecting the signal. So they cleaned the antenna, they shooed away the pigeons, they tested and retested, but the noise remained. It was faint, steady, coming from every direction in the sky, day and night, with no variation. It was a sound the universe itself was making. Penzias and Wilson didn't realize it at the time, but they had stumbled upon one of the greatest discoveries in the history of science. That faint hiss wasn't noise at all. It was the echo of the Big Bang. It was the cosmic microwave background, the very light that Gamow and his colleagues had predicted decades earlier. When the two astronomers finally learned what they had found, they were stunned. They won the Nobel Prize in Physics in 1978, not because they had been searching for the CMB, but because they had the patience and curiosity to investigate something they didn't understand. Sometimes the most profound truths arrive not through grand experiments, but through quiet persistence with the unexplained. What does this light actually look like? If you could see it, if you could paint it in colors, your eyes understand. It would appear as a soft, nearly uniform glow, like the inside of a perfectly smooth sphere surrounding you on all sides. But when scientists map it with incredible precision using satellites like COBE, WMAP, and Planck, they reveal something far more intricate. The CMB isn't perfectly smooth. It has tiny hot spots and cold spots variations in temperature of only a few millionths of a degree. These patterns aren't random. They carry information about the shape of the universe, about its age, about the forces that shaped it in those first moments. Some scientists describe the CMB as a baby picture of the cosmos, a snapshot taken when the universe was only a fraction of its current age. Others call it the universe's birth certificate, the most direct evidence we have of how everything began. And here's a thought that might make you pause just for a breath. This light, this ancient glow will outlast almost everything. Stars will die. Galaxies will drift apart. In trillions of years, when the last stars have burned out, and the universe has grown cold and dark, the cosmic microwave background will still be there, fainter than it is now, colder, but still traveling, still carrying the memory of that first moment when light was set free. It's the most patient storyteller the universe has ever known. It doesn't rush. It doesn't fade into nothing. It simply continues quietly, endlessly, like a lullaby that never quite ends. So, tonight as you rest, as your breathing slows and your thoughts begin to drift, remember this: you are not separate from the cosmos. You are held by the same light that filled the universe when it was young. That light has traveled across time itself to find you here, in this moment, in this quiet room. It doesn't ask for anything. It doesn't demand understanding. It simply touches you softly, the way the universe has always touched everything it holds. There's something deeply comforting in that isn't there. The idea that the oldest light in existence is still with us, still gentle, still glowing faintly in the dark. It's a reminder that even in a universe vast beyond comprehension, there are threads that connect everything. Light that remembers, silence that speaks, and a story that began long ago, still unfolding, still reaching out, still finding its way to you. But this is only the beginning. Because that moment when light was finally set free, when the universe became transparent for the first time, it wasn't just beautiful. It was a turning point, a threshold. And what happened in that instant would determine everything that came after. The shape of galaxies, the birth of stars, the possibility of worlds like ours. So, let's drift a little deeper. Let's return to that ancient moment, to the edge between fog and clarity, and see what it means when a universe opens its eyes for the very first time. There are moments in history that change everything, moments when something locked away is suddenly freed, when fog lifts, when silence breaks, when a door that has always been closed finally opens. The universe had such a moment, and it happened in an instant that lasted thousands of years. Imagine being trapped in a crowded room so dense you can't move forward even an inch. Every time you try to step, you bump into someone. Every direction you turn, there's another body blocking your way. That's what it was like for light in the early universe. Photons, those tiny packets of energy we call light, were born in the searing heat of the Big Bang. But they couldn't travel. They couldn't escape. Because the universe back then wasn't made of atoms. It was made of plasma, a thick soup of free electrons and protons, charged particles crashing into each other endlessly. And every time a photon tried to move, it would collide with an electron, scatter, change direction, and crash into another one. Light was imprisoned by matter itself. The universe was glowing, blazing hot, but completely opaque. You couldn't see through it any more than you could see through a wall. This state lasted for hundreds of thousands of years. The universe kept expanding, kept cooling, but it was still too hot for atoms to form. Electrons and protons circled each other like dancers who couldn't quite hold hands. The temperature needed to drop below a certain threshold, a specific point where the energy of the particles would finally be low enough for them to bond. Scientists have calculated that threshold with remarkable precision, roughly 3,000 degrees Kelvin. At that temperature, something extraordinary happens. Electrons which had been zipping around wildly slow down, just enough to be captured by protons. They spiral inward, falling into orbit, and suddenly hydrogen atoms exist. Neutral atoms. Atoms that don't scatter light the way free electrons do. And in that instant, the universe transforms. The fog clears. Light, for the first time since the beginning, can travel freely. Astronomers call this moment recombination, even though it's technically the first time these particles combined. And it marks the birth of the cosmic microwave background, the light we still see today. But here's what makes this moment so profound, so quietly beautiful. It didn't happen all at once everywhere, like flipping a switch. The universe is vast, and even though the conditions for recombination were met across the cosmos around the same time, the process unfolded gradually, like dawn breaking slowly across a landscape. In some regions, atoms formed slightly earlier, in others, slightly later. This created subtle variations, tiny differences in density and temperature that would later become the seeds of galaxies. But in the grand sweep of cosmic time, recombination happened in what feels like a single breath. 380,000 years after the Big Bang, the universe opened its eyes. And it has been transparent ever since. Think about what this means. Before recombination, the universe had no structure you could see. No stars, no galaxies, no planets. Just a formless glow uniform and unchanging. But the moment light was freed, the universe gained something it had never had before: the ability to be witnessed, to be seen. Of course, there were no eyes yet, no observers, no minds to perceive what was happening. But the possibility of sight was born in that moment. The universe became a place where light could carry information across vast distances, where shadows could form, where contrast and detail could exist. It's almost as if the cosmos needed to become transparent in order to tell its own story. And perhaps that's exactly what happened. Scientists have tried to describe what it would have been like to experience recombination if you could somehow be there. Imagine standing in a thick glowing fog, unable to see more than a few feet in any direction. The air around you hums with energy, shimmering with heat. Everything is bright, too bright to look at directly, but you can't see through it. And then gradually the fog begins to thin. At first you notice only small changes, a slight clearing here, a hint of depth there, but then suddenly the fog lifts entirely. You can see. The universe spreads out before you, vast and open, filled with faint ripples and waves, the echoes of ancient density fluctuations. The light that had been trapped for so long is now free, streaming outward in every direction, carrying with it the memory of that moment. It's a kind of birth, a kind of awakening. The universe learning to be visible. Now here's something that often confuses people, something worth pausing over for just a moment. Recombination doesn't mean the universe suddenly became cold. 3,000 Kelvin is still incredibly hot, far hotter than the surface of Venus, hotter than molten lava. If you could somehow touch the universe at that moment, you would be vaporized instantly. But by cosmic standards, it was cool enough. Cool enough for atoms to survive. Cool enough for light to escape. And that's all that mattered. The universe had crossed a threshold, and there was no going back. From that point forward, it would continue to cool, continue to expand, but it would always remain transparent. The prison doors had opened, and light would never be trapped again. What's remarkable is how precisely scientists can measure this transition. The temperature at which recombination occurred, the density of matter at that time, the speed at which the universe was expanding, all of these values can be calculated from observations of the cosmic microwave background. Satellites like WMAP and Planck have mapped the CMB with such accuracy that we can see the fingerprints of recombination written across the sky. Those tiny temperature fluctuations, those subtle hot and cold spots, they tell us exactly how dense different regions of the universe were when light was first released. And from that information, we can reconstruct the entire history of the cosmos, tracing it back to moments after the Big Bang itself. It's like reading a message written in the language of light, a message that has been traveling toward us for nearly 14 billion years. But there's a deeper question here, one that scientists still grapple with. Why did recombination happen at all? Why did the universe cool in just the right way, at just the right rate to allow atoms to form? If the expansion had been even slightly faster, the temperature might have dropped too quickly and the universe would have become too diffuse for atoms to bond. If the expansion had been slower, the universe might have remained hot and dense for too long, collapsing back in on itself before stars could ever ignite. The fact that recombination occurred at precisely the moment it did, and precisely the way it did, feels almost fine-tuned. Some physicists see this as evidence of deeper laws underlying principles we don't yet fully understand. Others see it as cosmic luck, a fortunate roll of the dice. Either way, it's a reminder that the universe we live in is not inevitable. It's the result of countless delicate balances, each one necessary for the next step to unfold. There's a beauty in that fragility, isn't there? The idea that everything we know, everything we see depended on a single transition happening at just the right temperature at just the right time. If recombination had failed, if atoms had never formed, the universe would be a very different place. No stars to fuse hydrogen into heavier elements. No planets to gather that matter into worlds. No life to wonder at the sky. The universe would remain a glowing fog, formless and empty, with no structure, no complexity, no memory. But because recombination succeeded, because light was freed, the cosmos became a place where stories could be written in starlight, where galaxies could bloom like flowers in slow motion, where minds could emerge and look back at the beginning, trying to understand how it all came to be. And here's something else worth holding for a moment. The light released during recombination, the cosmic microwave background, is the oldest light we can ever observe. It's the farthest back we can see. Before recombination, the universe was opaque, which means we can't use light to study anything earlier. It's like trying to see through a thick fog. No matter how powerful our telescopes, no matter how advanced our instruments, we can't see past that moment when the fog lifted. The CMB is the edge of our visible universe, the boundary between what can be known through observation and what must be inferred through theory. Some scientists call it the surface of last, scattering the place where photons last interacted with matter before traveling freely to us. It's a wall, but it's also a window. It shows us the universe at its youngest observable moment, and in doing so, it reveals the conditions that shaped everything that came after. But the story doesn't end with recombination, because those photons freed from their plasma prison didn't just stop. They kept traveling. They kept moving through the expanding universe, stretching and cooling as space itself grew larger. And over billions of years, those photons transformed. The light that was once visible, glowing bright and hot, shifted into infrared, then into microwaves, growing fainter and colder with every passing eon. Today, that light is still here, still traveling, still carrying the memory of recombination. It surrounds us constantly, a faint whisper of warmth in the cold expanse of space. And when we measure it, when we map it with our satellites and telescopes, we're not just seeing ancient light. We're seeing the moment the universe became itself, the moment it learned to shine. Have you ever thought about what it means to look back in time? When you observe the cosmic microwave background, you're not seeing the universe as it is now. You're seeing it as it was nearly 14 billion years ago, when it was still young, still simple, still in the process of becoming. The light has taken all this time to reach you, crossing unimaginable distances. And in that journey, it has carried the story of recombination forward through the ages. In a way, the CMB is a kind of time machine, the only one we have. It lets us witness an event that happened long before stars existed, long before planets formed, long before anything resembling life had even the faintest possibility of arising. And it does this not through guesswork or imagination, but through direct observation. The light is the evidence. The light is the proof. So, as you rest tonight, as your thoughts begin to drift and the world around you grows quieter, picture that moment. Picture the universe glowing and dense, filled with trapped light that couldn't escape. And then picture the slow, cooling, the gradual drop in temperature, the instant when electrons and protons finally came together, forming atoms for the first time. Picture the fog lifting the light, breaking free, streaming outward in every direction, carrying with it the memory of that transformation. That light is still traveling. It will always be traveling, and some of it right now, at this very second, is passing through you. The universe opened its eyes, and it has been watching itself ever since. But what did it see? What patterns emerged in that newly transparent cosmos? What tiny imperfections? What subtle ripples began to pull matter together, setting the stage for stars and galaxies and worlds like ours? The answers lie in the light itself, in the details hidden within the cosmic microwave background. And those details, as we'll discover, hold the blueprint for everything that came after. Sometimes the most important discoveries in history happen by accident, not because someone was searching for greatness, but because they refused to ignore something small, something strange, something that didn't quite make sense, a noise that wouldn't go away, a hiss in the background, a mystery too stubborn to dismiss. In the spring of 1964, two radio astronomers named Arno Penzias and Robert Wilson were working at Bell Telephone Laboratories in Holmdel, New Jersey. They had a job that seemed simple enough: calibrate a large horn-shaped antenna originally built for satellite communications. The antenna looked a bit like an enormous ear pointed at the sky, and their task was to measure radio signals with as much precision as possible. But there was a problem. No matter what they did, no matter how carefully they adjusted the equipment, there was always a faint hiss, a persistent background noise. It came from every direction day and night, without variation. At first, they assumed it was interference from New York City, just 30 miles away, urban noise bleeding into their measurements. But when they pointed the antenna away from the city, the hiss remained. Same volume, same frequency. Unshakable. They began to suspect the antenna itself. Maybe something was wrong with the equipment. Maybe there were electronic glitches or thermal irregularities throwing off the readings. So they tested everything. They checked the wiring. They examined the circuitry. They measured the temperature of every component. Still, the noise persisted. And then one day they noticed something peculiar. A pair of pigeons had nested inside the horn antenna. Pigeons. Living there quite comfortably, leaving behind what Penzias later described with characteristic understatement as a white dielectric material. In other words, pigeon droppings. Maybe that was the source of the interference. Maybe the pigeons were somehow distorting the signal. It seemed like a reasonable explanation. So they captured the pigeons, cleaned out the antenna, thoroughly scrubbing away every trace of the bird's presence. They released the pigeons far away, hoping they wouldn't return. But the pigeons came back. They nested again. So Penzias and Wilson repeated the process, this time more decisively. And once the antenna was completely clean, once the pigeons were permanently gone, they turned the system back on. And the hiss was still there, unchanged, unmoved, as if the universe itself was humming a song they couldn't turn off. At this point, many scientists might have given up, might have dismissed the noise as a technical flaw, an unsolvable quirk of the equipment. But Penzias and Wilson didn't do that. They kept investigating. They kept asking questions. And eventually they reached out to colleagues searching for answers. It was then that they learned something extraordinary. A team of physicists at Princeton University, led by Robert Dicke, had been working on a theory. They predicted that if the Big Bang had really happened, if the universe truly began in a hot, dense state, then there should be leftover radiation from that early period, a kind of thermal echo. This radiation would have cooled over billions of years as the universe expanded, shifting from visible light to infrared and finally to microwaves. Dicke's team had even calculated what temperature this radiation should have, around 3 degrees Kelvin. and they were planning to build an antenna to search for it. But when Dicka heard about the persistent noise Penzias and Wilson had found, he realized something profound. The search was over. The echo had already been discovered. When his colleague informed him of the news, Dicka turned to his team and said simply, "Well, boys, we've been scooped." It wasn't bitterness. It was recognition. The universe had spoken, and someone else had been listening. The hiss that Penzias and Wilson couldn't explain was the cosmic microwave background, the oldest light in the universe, the afterglow of creation itself. They hadn't been looking for it. They had no expectation of finding anything so monumental. They were just trying to eliminate noise from their measurements, and in doing so, they stumbled upon one of the greatest discoveries in the history of astronomy. In 1978, Penzias and Wilson were awarded the Nobel Prize in Physics, not for seeking glory, but for paying attention, for refusing to dismiss what they didn't understand, for trusting that even the smallest mystery might hold the largest truth. But here's what makes this story even more remarkable. The prediction that the cosmic microwave background should exist had been made decades earlier. In 1948, a physicist named George Gamow, along with his colleagues Ralph Alpher and Robert Herman, published a paper predicting that the early universe would have left behind thermal radiation. They calculated its temperature. They described its properties. They even suggested it should be detectable with the right equipment, but their work was largely ignored. The idea of the Big Bang was still controversial. Many scientists preferred the steady-state theory, which proposed that the universe had always existed in roughly the same form, with no beginning, no explosive origin. Gamow's prediction was too strange, too radical. It didn't fit the prevailing assumptions. So, it sat in the scientific literature, mostly forgotten, waiting for someone to take it seriously. When Penzias and Wilson made their discovery, Alpher and Hermann were still alive. They had spent years knowing the CMB should be out there, but without the recognition or resources to prove it. The discovery vindicated their work, but it also carried a kind of quiet sadness. They had seen the answer first, but the world hadn't been ready to listen. This happens more often than you might think in science. Predictions made too early. Theories proposed before the technology exists to test them. Ideas dismissed because they seem too bold, too unlikely, too far removed from common sense. And then years later, sometimes decades later, the evidence appears. The noise becomes a signal. The mystery becomes a revelation. It's a reminder that the universe doesn't care about our timelines. It doesn't wait for us to be ready. It simply is. And if we're patient, if we keep looking, keep questioning, keep paying attention to what doesn't quite fit, eventually the truth finds a way through. Now, here's a question worth holding for a moment. What would have happened if Penzias and Wilson had dismissed the hiss? What if they had concluded it was just equipment error and moved on? The cosmic microwave background would still be there, of course. The light would still be streaming through space, carrying the memory of the early universe. But we might not have found it for years, maybe decades. The entire history of cosmology could have unfolded differently. We might still be debating whether the Big Bang really happened. We might still be clinging to theories that don't match reality. The discovery of the CMB didn't just confirm the Big Bang, it transformed our understanding of the universe. It gave us a way to study the cosmos when it was still an infant. It opened a door we didn't even know was there. And it happened because two people refused to ignore a noise. There's a deeper lesson in that. Science isn't just about grand theories or complex mathematics. It's about paying attention. It's about noticing the small things, the anomalies, the details that don't quite fit. It's about having the humility to say, I don't know what this is, but I want to find out. Penzias and Wilson weren't trying to revolutionize cosmology. They were just trying to get rid of static. But their curiosity, their persistence, their refusal to accept easy answers led them to something far greater. And in a way, that's how most discoveries happen, not through brilliance alone, but through patience, through stubbornness, through the quiet determination to understand what the universe is trying to say. After the discovery was confirmed, Scientists around the world began studying the cosmic microwave background in earnest. They built new instruments, designed new experiments, launched satellites into space to map the CMB with ever greater precision. Each generation of observation revealed more detail, more structure, more information hidden within the ancient light. In 1989, NASA launched the Cosmic Background Explorer, or COBE, which measured the CMB's temperature with unprecedented accuracy and detected the tiny fluctuations that hinted at the seeds of galaxies. The project's lead scientist, George Smoot, famously described the results as seeing the face of God, a poetic way of saying they had glimpsed the blueprint of creation. In 2001, the Wilkinson Microwave Anisotropy Probe, WMAP, refined those measurements even further, mapping the CMB across the entire sky and providing data that would reshape our understanding of the universe's age composition and fate. And in 2009, the European Space Agency launched Planck, the most sensitive CMB observatory ever built, capable of detecting temperature variations as small as a few millionths of a degree. Each of these missions built on the accidental discovery made in a pigeon-filled antenna in New Jersey. Each one carried forward the legacy of that persistent hiss. But there's something almost poetic about the way the CMB was found. Not in a gleaming laboratory, not with the most advanced technology of the time, but in a modest antenna surrounded by pigeons by two scientists who just wanted to understand why their equipment wouldn't stop humming. It's a story that reminds us that the universe doesn't reveal its secrets only to those who seek them. Sometimes it whispers to those who are simply listening, and sometimes the greatest discoveries come not from looking harder, but from refusing to look away. Think about what that means for a moment. The echo of the Big Bang, the oldest light in existence, the most direct evidence we have of how the universe began, was discovered because two people took a mystery seriously. Because they didn't give up. Because they trusted that the noise meant something. And it did. It meant everything. It meant the universe had a beginning. It meant space itself had been expanding for billions of years. It meant the story we told about the cosmos could be tested, measured, confirmed. The CMB wasn't just a discovery. It was proof. Proof that the universe remembers. Proof that the past is still here, still glowing faintly in the dark, still waiting to be understood. So, tonight as you rest, as your mind drifts between waking and sleep, think about that antenna in New Jersey. Think about the pigeons nesting inside, unaware that they were sharing space with one of the most important instruments in the history of science. Think about the hiss, the faint, steady hum that wouldn't go away. And think about the fact that sometimes the universe speaks in whispers, in background noise, in things we almost overlook. It doesn't shout, it doesn't demand attention. It simply hums quietly, patiently, waiting for someone to notice. And when we do notice, when we stop and listen, when we take the time to ask what that hum might mean, the universe opens up. It tells us where it came from. It shows us what it looked like when it was young. It offers us a glimpse of the moment when everything began. The discovery of the cosmic microwave background wasn't just a triumph of science. It was a triumph of curiosity, of persistence, of the willingness to investigate what doesn't make sense. And in many ways, that's what science is. A long, patient conversation with the universe. A conversation that began with a question, a mystery, a noise that wouldn't stop. And continues still, each new observation adding another word, another sentence, another chapter to the story we're trying to understand. But what exactly were Penzias and Wilson hearing? What does the cosmic microwave background actually look like when you map it across the entire sky? What patterns emerge when you measure it with enough precision? The answers to those questions would reveal something even more astonishing than the discovery itself. They would show us not just that the universe had a beginning, but what that beginning looked like, and what it would one day become. If you could see with different eyes, if your vision could shift beyond the narrow band of light we call visible, the night sky would tell a different story. It wouldn't be dark. It wouldn't be scattered with stars. Instead, it would glow softly, evenly in every direction, like the inside of a perfect sphere painted in a single uniform color. That's what the cosmic microwave background looks like. A blanket of ancient light draped across the entire universe, glowing at a temperature so precise, so consistent, it feels almost impossibly perfect. When scientists first measured the CMB with enough accuracy to map it across the sky, they discovered something astonishing. The temperature of this ancient light is nearly the same everywhere. No matter which direction you point your instruments, no matter what time of day or night, the CMB hovers around 2.725 Kelvin. That's about minus 270 degrees Celsius, just a few degrees above absolute zero. The coldest temperature theoretically possible. It's a whisper of warmth in the vast coldness of space. And yet, it's there. Always there, surrounding us, touching everything. Some scientists describe it as the most perfect thermal radiation ever observed in nature, a black-body spectrum so precise it follows the laws of physics with almost flawless elegance. The universe, it seems, knows how to cool down gracefully, evenly, without hurry. But here's where the story gets even more intriguing. If you measure the CMB with extraordinary sensitivity, if you look closely enough, you'll notice something subtle. Tiny fluctuations. Small variations in temperature from one patch of sky to another. These differences are incredibly faint, only about 1 part in 100,000. Imagine a perfectly smooth surface, and then imagine placing grains of sand on it, so small you can barely tell they're there. That's what the CMB fluctuations are like. If the average temperature is 2.725 Kelvin, these hot and cold spots differ by only a few millionths of a degree. You would never notice them without the most sensitive instruments humanity has ever built. And yet, they are the most important features of the CMB, because those tiny ripples, those faint imperfections, are the seeds of everything that came after. They mark the places where matter was just a little bit denser, where gravity pulled just a little bit harder, where the first stars would one day ignite. Without those ripples, the universe would have remained smooth, lifeless, empty. But because of them, galaxies formed, planets formed, you formed. When the COBE satellite first detected these temperature fluctuations in 1992, the scientific community was stunned. Not because the fluctuations existed, they had been predicted, but because of how precisely they matched theoretical models. The data showed that the early universe wasn't perfectly uniform. It had structure-subtle variations that would grow over billions of years into the cosmic web of galaxies we see today. George Smoot, one of the lead scientists on the COBE mission, described the moment of discovery with a kind of reverence. He said it was like looking at the face of God, not in a religious sense, but in the sense that they were seeing the blueprint of creation itself. The CMB wasn't just light from the past. It was a map, a detailed, intricate map showing where the universe had been and where it was going. And it was written in temperature in the faintest of glows in patterns so delicate they almost seemed designed. But what do these patterns actually mean? Why does a tiny difference in temperature matter so much? To understand this, you have to think about gravity. In the early universe moments after recombination, matter was spread out almost evenly, but not quite. In some regions, there was slightly more hydrogen, slightly more helium, just a tiny excess of mass. And where there was more mass, there was more gravitational pull. That pull attracted nearby matter, drawing it inward slowly over millions of years. The denser regions grew denser. The emptier regions grew emptier. Those small fluctuations amplified over time like ripples spreading across a pond until they became the large-scale structures we observe today. Galaxy clusters, superclusters, vast filaments of matter stretching across hundreds of millions of light years. The CMB captured the universe at the very beginning of this process, before any stars had formed, before any galaxies had taken shape. It shows us the raw ingredients, the initial conditions, the starting point of everything. And those starting points were written in temperature differences so small, you'd need instruments capable of measuring changes of a few millionths of a degree to see them. The technology required to map the CMB with this level of precision is almost beyond comprehension. Satellites like WMAP and Planck orbit far above Earth's atmosphere, shielded from interference, equipped with detectors cooled to temperatures colder than deep space itself. These instruments measure microwave radiation coming from every direction in the sky, pixel by pixel, building up an image that looks at first glance almost abstract. When you see a map of the CMB, it's usually displayed in false colors, reds and oranges representing slightly warmer regions, blues and purples representing slightly cooler ones. The differences are exaggerated so we can actually see them. In reality, the entire sky glows at nearly the same temperature. But those exaggerated maps reveal something profound. They show that the universe, even in its infancy, was not random. It had patterns. It had order. It had the beginnings of structure. One of the most striking features of the CMB is how uniform it is on large scales. If you average the temperature across vast regions of the sky, the differences almost disappear. This tells us that the early universe was incredibly smooth, far smoother than anything we see today. Galaxies are clumped together, stars are scattered unevenly. But the CMB is nearly the same temperature everywhere, which suggests that the universe began in a state of remarkable equilibrium. Some scientists find this puzzling. How could regions of space separated by billions of light-years regions that could never have been in contact with each other end up at almost exactly the same temperature? This is known as the horizon problem, and it's one of the reasons physicists developed the theory of cosmic inflation, a brief period of exponential expansion in the first fraction of a second after the Big Bang. Inflation would have stretched tiny regions of space that were once in thermal equilibrium to enormous sizes, smoothing out the universe and explaining why the CMB looks so uniform. The patterns we see, those tiny fluctuations, would then be the result of quantum fluctuations during inflation, stretched to cosmic scales and frozen into the fabric of space itself. But here's something that often gets misunderstood. The cosmic microwave background is not the Big Bang. It's not the moment of creation. It's the light released 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light to travel freely. Before that moment, the universe was opaque, a glowing fog we can't see through. The CMB is the earliest observable moment, the edge of our visible universe. Everything before it is hidden behind that wall of light. We can't use telescopes to see further back, no matter how powerful they are. The CMB is both a window and a barrier. It shows us the universe as an infant, but it also marks the limit of what we can observe directly. Anything earlier than recombination must be inferred from theory, from mathematics, from the subtle clues encoded in the patterns of the CMB itself. And those clues, when studied carefully, reveal astonishing things. For example, by analyzing the size and distribution of the temperature fluctuations, scientists can determine the geometry of the universe. Is space flat, curved inward like a sphere, or curved outward like a saddle? The answer, confirmed by measurements from WMAP and Planck, is that the universe is remarkably flat. Not perfectly flat, but close enough that on the largest scales, space behaves as if it extends in straight lines forever. This was not a foregone conclusion. Before these measurements, many scientists thought the universe might be curved, might eventually collapse back in on itself, or expand forever in a hyperbolic shape. But the CMB data settled the question. If the universe is flat, or so close to flat, that the difference doesn't matter for most purposes. And this flatness has profound implications for the fate of the cosmos, for how galaxies will evolve, for whether the universe will continue expanding indefinitely or eventually slow down. The CMB also tells us about the composition of the universe. By studying the patterns of the fluctuations, scientists can determine how much of the universe is made of ordinary matter, the atoms and molecules we're familiar with. And how much is made of dark matter, an invisible substance that interacts only through gravity and dark energy, a mysterious force driving the accelerated expansion of space. The results are humbling. Ordinary matter, the stuff that makes up stars, planets, and people, accounts for only about 5% of the universe's total mass and energy. Dark matter makes up roughly 27%. And dark energy, the strangest component of all, makes up about 68%. The CMB doesn't just show us what the universe looked like when it was young, it reveals what the universe is made of. And most of it is invisible, most of it is unknown, most of it is still a mystery. Have you ever thought about what it means to see something so old? When you look at the CMB, you're not seeing the universe as it is now. You're seeing it as it was, nearly 14 billion years ago, when it was still simple, still uniform, still in the earliest stages of becoming what it would one day be. The light has taken all this time to reach us, crossing unimaginable distances, stretching and cooling as space itself expanded. And in that journey, it has carried the memory of the early universe forward through the ages. The CMB is a kind of time capsule, a message sent from the distant past, written in the language of temperature and light. And we are only just beginning to learn how to read it. But the story doesn't end with smooth, nearly uniform glow. Because hidden within the CMB, encoded in those tiny fluctuations, are clues to something even deeper. Clues to the very first moments after the Big Bang, when the universe was smaller than an atom, when quantum mechanics and gravity danced together in ways we're still trying to understand. The patterns we see in the CMB are not random. They are the fingerprints of those earliest moments stretched across the sky, waiting to be deciphered. And when we study them closely, when we measure them with the utmost precision, they tell us something extraordinary. They tell us that the universe, for all its vastness, for all its complexity, began in a state of almost perfect simplicity, a state so delicate, so finely balanced, that the slightest variation could have changed everything. So, as you rest tonight, as your thoughts begin to drift and the world around you grows quieter, picture that map. Picture the cosmic microwave background spread across the entire sky, glowing softly at 2.725 Kelvin, nearly the same temperature everywhere, with only the faintest ripples to mark where galaxies would one day form. Picture the satellites orbiting far above Earth, measuring those ripples, mapping them pixel by pixel, building up an image of the universe when it was still an infant. And picture the scientists studying that image, tracing the patterns, reading the clues, trying to understand how everything began. The CMB is more than data. It's more than numbers on a screen. It's the universe's birth certificate, its autobiography, its way of saying, this is where I came from, this is what I looked like when I was young, this is the story of how I became myself. And that story, as we'll see, is written not just in the glow of the CMB, but in the way that glow has changed over time, in the way light stretches and cools as the universe expands, in the way temperature drops degree by degree across billions of years. The CMB wasn't always at 2.725 Kelvin. Once it was much hotter. And understanding how it cooled, how it transformed from blazing light to faint microwaves, reveals something fundamental about the nature of space itself. Imagine holding a piece of metal in a fire until it glows red hot, then pulling it out and watching as it cools. At first, it radiates visible light, bright orange, then red, then dimmer and dimmer, until you can no longer see it glowing, though it's still warm to the touch. The light hasn't disappeared, it's just shifted into wavelengths your eyes can't detect. Infrared, then far infrared, fading into longer and longer waves as the heat dissipates. That's essentially what happened to the universe. It started hot blazing with light, and over billions of years it cooled, and the light stretch dimmed, transformed until it became the faint microwave glow we detect today. When the cosmic microwave background was first released, when light finally broke free during recombination, the universe was glowing at a temperature of roughly 3,000 Kelvin. That's about the temperature of a red dwarf star's surface, hot enough to make everything shine with a soft reddish-orange glow. If you could have been there, if you could somehow witness that moment, the sky wouldn't have been dark. It would have been filled with light, not the brilliant white of our sun, but a deep, warm radiance like standing inside a furnace that stretched infinitely in every direction. And then, as the universe continued to expand, something remarkable happened. The light began to stretch. Not because the photons themselves were changing, but because the space they were traveling through was growing larger. And as space expanded, the wavelengths of light expanded, with it shifting from visible light into the infrared and eventually into microwaves. This process is called cosmological redshift, and it's one of the most profound consequences of living in an expanding universe. Think of it like this. Imagine you're listening to the sound of an ambulance siren as it drives past you. When it's approaching, the sound waves are compressed, making the pitch higher. When it's moving away, the sound waves are stretched, making the pitch lower. This is the Doppler effect, something you've probably experienced countless times without thinking about it. Cosmological redshift works in a similar way, except instead of an object moving through space, it's space itself that's expanding, carrying galaxies, stars, and light along with it. As the universe grows, the distance between any 2 points increases, and light traveling through that expanding space gets stretched. The wavelength increases, the frequency decreases, and the energy of the light drops. A photon that started as visible light billions of years ago has been stretched so much by now that it arrives as a microwave invisible to the eye, detectable only with specialized instruments. The universe has been cooling down for 13.8 billion years, and the CMB is its temperature record, a fever chart written in light. Scientists can calculate exactly how much the universe has expanded since recombination by comparing the temperature then to the temperature now. The ratio is straightforward. The CMB was emitted at about 3,000 Kelvin, and today it's measured at 2.725 Kelvin. Dividing those numbers gives you roughly 1,100, which means the universe has expanded by a factor of about 1,100 since the moment light was first freed. Everything was 100 times closer together back then. Galaxies that are now billions of light years apart were once separated by distances 1,000 times smaller. And the light we see today, the faint microwave glow surrounding us, is a direct consequence of that expansion. It's not that the light has grown old or tired. It's that the universe has grown larger, and the light has stretched to fill the new space. There's something almost poetic about that, isn't there? The idea that light doesn't fade because it loses energy in the traditional sense, but because the canvas it's painted on keeps expanding. Imagine drawing a picture on a balloon and then inflating it. The picture doesn't disappear, but it spreads out, becomes less dense, less concentrated. The colors don't change fundamentally, but the details stretch, the lines grow thinner, the image becomes more diffuse. That's what's happening to the CMB. The light is still there, still carrying the memory of the early universe, but it's been stretched across a space far larger than it was when it began its journey. And because of that stretching, what was once a brilliant glow has become a faint whisper, a background hum so subtle we didn't even know it existed until we built the instruments sensitive enough to detect it. Now, here's where the science gets beautifully precise. The relationship between temperature and wavelength follows a well-understood law in physics called Wien's displacement law. It states that as an object cools, the peak wavelength of the light it emits shifts toward longer wavelengths. Hot objects glow blue or white. Cooler objects glow red. Even cooler objects emit infrared. And the coolest objects, like the cosmic microwave background, emit microwaves. By measuring the spectrum of the CMB, scientists can determine its temperature with extraordinary accuracy. The Planck satellite, for instance, measured the CMB temperature to be 2.72548 Kelvin plus or minus a tiny fraction of a degree. That level of precision is astonishing. It tells us not just that the universe is cooling, but exactly how cool it has become. and by extension how much it has expanded since recombination. Every decimal point matters. Every measurement refines our understanding of cosmic history. But there's a common misunderstanding worth addressing here. Some people assume that the CMB is cold because it's old, as if light naturally loses energy over time the way a battery runs down. But that's not quite right. The CMB is cold because the universe has expanded. If the universe had stopped expanding billions of years ago, the CMB would still be glowing at a much higher temperature. The cooling is a direct result of the stretching of space itself. It's a consequence of cosmology, not entropy in the usual sense. The photons haven't lost energy to friction or heat dissipation. They've been redshifted, stretched, diluted across an ever larger volume of space. And that distinction matters. It tells us that the universe isn't just a static container where things happen. It's dynamic, it's growing, and everything within it, including light itself, is shaped by that growth. There's another fascinating detail hidden in the temperature of the CMB. It's not uniform everywhere. If you measure it carefully, you'll notice a slight asymmetry, a pattern called the dipole anisotropy. On one side of the sky, the CMB is very slightly warmer, about 0.0335 Kelvin hotter than average. On the opposite side, it's slightly cooler by the same amount. This isn't a feature of the early universe. It's a result of our motion through space. The Milky Way galaxy, along with the solar system and Earth, is moving at about 370 kilometers per second relative to the CMB's rest frame. As we move toward one direction, the light in that direction gets blue-shifted, compressed, making it appear slightly warmer. The light behind us gets red-shifted, stretched, making it appear slightly cooler. It's the Doppler effect again, but on a cosmic scale. By measuring this, dipole scientists can determine not just that we're moving, but exactly how fast and in which direction. We're drifting through the universe at hundreds of kilometers per second, carried along by the gravitational pull of distant galaxy clusters. And the CMB reveals that motion with perfect clarity. Once you account for this dipole, once you subtract our motion through space, what remains are the intrinsic fluctuations in the CMB, those tiny variations of a few millionths of a degree that mark the seeds of galaxies. And those fluctuations also tell us about temperature, but in a different way. They show us that even in the early universe, not every region was at exactly the same temperature. Some areas were slightly denser, which made them slightly warmer. Others were slightly less dense, slightly cooler. And those small differences, amplified by gravity over billions of years, became the large-scale structures we see today. The temperature variations in the CMB are a map of the universe's destiny, written when it was still an infant. Let's pause for a moment and think about what this means. The light we detect today, the cosmic microwave background at 2.725 Kelvin, was once blazing hot, glowing at 3,000 Kelvin. Over 13.8 billion years, it has cooled by a factor of more than 1,000. And it's still cooling. Every moment as the universe continues to expand, the CMB grows colder, its wavelength stretches a little more, its energy decreases by an infinitesimal amount. In another billion years, the temperature will drop further. In 100 billion years, it will be even colder. Eventually, trillions of years from now, the CMB will fade to a temperature so low, it will be almost indistinguishable from absolute zero. But it will never quite reach zero. It will always be there, a faint glow in the darkness, a memory that refuses to fade completely. The universe will carry this light with it forever, no matter how cold it becomes. There's something deeply moving in that thought. The idea that the universe is slowly cooling, slowly fading, but never quite letting go of its past. The CMB is a kind of cosmic memory, a record of where the universe has been, and that record will persist long after stars have burned out, long after galaxies have drifted beyond each other's horizons, long after the last light of the last star has flickered into darkness. The universe will still remember its beginning. It will still hold on to that first moment when light was freed. And in that sense, the CMB is eternal, not unchanging, but enduring, patient, waiting. But the temperature of the CMB doesn't just tell us about the past, it also tells us about the future. By measuring how the CMB has cooled over time, by understanding the relationship between expansion and redshift, scientists can project forward, predicting what the universe will look like billions of years from now. And the picture isn't comforting, but it is beautiful in its own way. The universe will keep expanding faster and faster, driven by dark energy. Galaxies will drift apart, stars will exhaust their fuel, and the CMB will continue to cool, its temperature dropping asymptotically towards zero, never quite reaching it, but getting closer with every passing eon. Eventually, the universe will enter what some physicists call the heat death, a state where entropy has maximized, where no energy is available to do work, where everything has reached the same cold, uniform temperature. And even then, the CMB will still be there, a faint echo of the moment when everything began. Does that thought make you uneasy, or does it offer a strange kind of comfort? There's something almost reassuring in the idea that the universe doesn't forget, that even as it cools, even as it fades, it carries the memory of its origin with it. The CMB is proof that the past isn't gone. It's still here, still glowing faintly in the dark, still touching everything, and in a way that makes the universe feel less empty, less lonely. It's a place with a history, with a story, with a beginning that it remembers and honors simply by existing. So, tonight as you rest, as your breathing slows and your mind begins to drift, think about that cooling. Think about the light that was once hot enough to glow red-orange, now stretched and cooled into faint microwaves. Think about how the universe has been expanding for 13.8 billion years, carrying that light with it, letting it stretch and cool and fade, but never letting it disappear. The temperature of the CMB is not just a number, it's a measure of time, a measure of growth, a measure of how far the universe has come since it was young. And it's still changing, still cooling, still telling its story in the quietest possible way. But there's more to the story than just cooling, because those tiny temperature variations, those faint fluctuations we've mentioned, they weren't random. They had a cause. They were imprinted on the CMB by processes that happened in the very first moments after the Big Bang, when the universe was smaller than an atom, when quantum mechanics ruled everything. And understanding where those fluctuations came from, why they exist at all, reveals something astonishing about the nature of reality itself. What if I told you that the reason you exist, the reason anything exists, is because the universe made a mistake? Not a catastrophic error, but a tiny imperfection, a subtle flaw in an otherwise smooth beginning. Without that flaw, the cosmos would have remained featureless, lifeless, empty. But because of it, stars ignited. Galaxies spiraled into being. Worlds formed, and eventually minds emerged to wonder why. Sometimes imperfection is the only path to beauty. The early universe, as we've seen, was remarkably smooth, almost perfectly uniform. When recombination happened and light was finally freed, the temperature of the cosmic microwave background was nearly the same, everywhere varying by only about 1 part in 100,000. That's an astonishing level of uniformity. Imagine spreading a layer of paint across a surface the size of Earth, and having the thickness vary by less than the width of a human hair. That's how smooth the early universe was. And yet, those tiny variations, those barely perceptible differences were enough. They were the seeds, the sparks, the quiet beginnings of everything that would come after. Scientists call them anisotropies, a technical term that simply means the universe wasn't quite the same in every direction. And those anisotropies, as faint as they were, changed everything. But where did they come from? Why did the universe have these tiny imperfections at all? For years, physicists puzzled over this question. If the Big Bang began from a single point, if everything emerged from the same initial conditions, why wasn't the universe perfectly smooth? Why were there fluctuations? The answer, as it turns out, lies in one of the strangest and most beautiful aspects of reality, quantum mechanics. In the very first moments after the Big Bang, the universe was unimaginably small, smaller than an atom, smaller than a proton, perhaps as small as the Planck length, the smallest meaningful distance in physics. At that scale, quantum effects dominate. And at the quantum level, nothing is ever perfectly smooth. Even empty space fluctuates. Tiny ripples of energy appear and disappear, virtual particles pop into existence for the briefest of moments before vanishing again. Physicists call these quantum fluctuations, and they're a fundamental feature of reality. You can't eliminate them. They're woven into the fabric of the universe itself. Now, ordinarily, these quantum fluctuations are so small, so fleeting, that they don't have any lasting effect. They happen at scales far too tiny for us to notice. But in the earliest moments of the universe, something extraordinary occurred, a process called cosmic inflation, a brief period of exponential expansion that lasted only a fraction of a second, took those microscopic quantum fluctuations and stretched them to cosmic scales. Imagine taking a tiny wrinkle in a piece of fabric and pulling the fabric so fast, so violently, that the wrinkle becomes enormous spanning meters or kilometers. That's essentially what inflation did. Quantum fluctuations that began smaller than an atom were inflated to sizes larger than galaxies. And when inflation ended, those stretched fluctuations became frozen into the structure of space itself. They became the density variations we see in the cosmic microwave background, the hot spots and cold spots, the places where matter was slightly denser or slightly less dense, the seeds of everything. This is one of the most profound ideas in modern cosmology. The largest structures in the universe, the superclusters of galaxies, the vast cosmic web of matter stretching across hundreds of millions of light years, all of it originated from quantum fluctuations in the first tiny fraction of a second after the Big Bang. The quantum and the cosmic are connected. The smallest and the largest scales of reality are linked by inflation, by that brief moment of exponential growth that took randomness at the subatomic level and imprinted it across the entire observable universe. It's as if the universe began as a whisper, and inflation turned that whisper into a shout that still echoes today. But here's what makes this even more remarkable. The fluctuations weren't completely random. They followed specific patterns predicted by the physics of inflation and quantum field theory. When scientists analyze the CMB, when they study the size and distribution of the temperature variations, they find that the fluctuations match theoretical predictions with stunning accuracy. The anisotropies have a characteristic scale, a preferred size, determined by the physics of the early universe. Regions that were causally connected before inflation, meaning they were close enough to influence each other, left imprints in the CMB that we can measure today. And those imprints tell us about the conditions in the universe when it was less than a trillionth of a second old. We're reading messages written in the quantum foam of the newborn cosmos, and somehow impossibly the messages are clear. Let's think about what this means for a moment. The reason galaxies exist, the reason stars formed, the reason planets like Earth could coalesce and develop life, all of it traces back to quantum fluctuations. Randomness at the smallest scale became structure at the largest scale. Without those fluctuations, the universe would have remained perfectly smooth. Matter would have been spread evenly, with no denser regions to collapse under gravity, no places for stars to ignite. The universe would be a vast, dark ocean of hydrogen and helium uniform and unchanging, stretching forever without variation. No light, no warmth, no complexity, no possibility of observers to wonder about any of it. But because the quantum world is inherently uncertain, because fluctuations are unavoidable, the universe gained the potential for structure. Imperfection became the foundation for everything. There's a philosophical weight to that realization, isn't there? We often think of perfection as an ideal, something to strive for. But in cosmology, perfection would have meant emptiness. A perfectly smooth universe is a dead universe. It's the imperfections, the tiny deviations from uniformity that make life possible, that make anything possible. Scientists sometimes describe this as a kind of cosmic balance. If the fluctuations had been too large, matter would have clumped together too quickly, forming black holes everywhere, leaving no room for stars or galaxies to develop. If the fluctuations had been too small, gravity would have been too weak to pull matter together, and the universe would have remained diffuse, formless, unable to create anything. The fluctuations were just right, not too strong, not too weak, just enough to allow structure to emerge over billions of years. Some physicists see this fine-tuning as evidence of deeper principles we don't yet understand. Others see it as a fortunate accident. Either way, it's humbling. The universe exists in a narrow range of possibilities, and we happen to live in one where complexity can arise. Now, here's something that often gets misunderstood. When we talk about the fluctuations in the CMB, we're not talking about variations in light itself, but variations in the density of matter at the moment light was released. In regions where matter was slightly denser, gravity pulled harder, compressing the matter and heating it up, which made the CMB slightly warmer in those regions. In areas where matter was slightly less dense, the opposite happened, and the CMB appears slightly cooler. So, the temperature map of the CMB is really a density map of the early universe. It shows us where matter was clustered and where it was sparse. And over time, the denser regions grew denser. Gravity amplified the initial differences. Matter flowed toward the denser spots, leaving the less dense regions emptier. This process, called gravitational instability, is slow at first, but accelerates over time. After millions of years, those tiny overdensities became the first stars. After hundreds of millions of years, they became the first galaxies. After billions of years, they became the cosmic web, the intricate network of galaxy clusters and filaments we observe today. The entire large-scale structure of the universe can be traced back to those initial fluctuations, those quantum ripples frozen into the CMB. Let me give you a sense of scale. The fluctuations in the CMB correspond to density differences of about 1 part in 100,000. That means, if the average density of matter in the early universe was, say, 100,000 particles per cubic meter, the densest regions had about 100,001 particles, and the least dense regions had about 99,999. A difference of just 1 particle. That's how subtle the variations were. And yet, over 13 billion years, gravity turned that single extra particle into entire galaxies. It's like planting a seed so small you can barely see it and watching it grow into a forest. The universe is patient. It takes its time. But it never forgets the initial conditions. Every galaxy, every star, every atom in your body traces its lineage back to those tiny fluctuations in the cosmic microwave background. There's another layer to this story, one that connects quantum mechanics to cosmology in an even deeper way. The fluctuations we see in the CMB aren't just any random pattern. They have a specific statistical distribution, something called a nearly scale-invariant power spectrum. That's a technical way of saying the fluctuations look similar at different scales. Whether you're looking at small patches of the sky or large regions, the level of variation is roughly the same. This is exactly what inflationary theory predicts. During inflation, quantum fluctuations were stretched uniformly across all scales, creating a pattern that's self-similar, fractal-like in a sense. When scientists first measured the power spectrum of the CMB with the COBE satellite in the early 1990s, they found it matched inflationary predictions almost perfectly. It was a triumph for the theory, one of the strongest pieces of evidence that inflation really happened. And it meant that the quantum fluctuations we observe today, the seeds of galaxies, were once fluctuations in the quantum fields that filled the infant universe. The boundary between the quantum and the classical, between the microscopic and the cosmic, blurred in those first moments. And the CMB is the record of that blurring. But what would have happened if the fluctuations had been different? What if they had been perfectly smooth, with no variations at all? Or What if they had been much larger with wild swings in density? Scientists have run simulations to explore these alternate universes, and the results are striking. In a perfectly smooth universe, no structure forms. Galaxies never coalesce. Stars never ignite. The universe remains a cold, dark expanse of gas, slowly diluting as space expands. In a universe with very large fluctuations, structure forms too quickly. Matter collapses into black holes almost immediately before stars have a chance to form. Either way, there's no opportunity for complexity, no chance for planets, no possibility for life. We live in a universe where the fluctuations were just strong enough to create structure, but not so strong that structure formed too fast. It's a delicate balance, and it was set in the first fraction of a second after the Big Bang. Everything that happened afterward, everything that exists today, is a consequence of that balance. Have you ever thought about how strange it is that randomness could lead to order? That chaos at the quantum level could produce the intricate structures we see in the universe. It's counterintuitive. We usually think of randomness as destructive, as something that erodes patterns rather than creating them. But in cosmology, randomness is generative. The quantum fluctuations weren't noise. They were signal. They were the raw material from which everything else emerged. And in that sense, the universe is fundamentally creative. It takes uncertainty and turns it into stars. It takes imperfection and builds galaxies. It starts with nothing but energy and quantum foam and ends with worlds where minds can look up at the sky and wonder how it all began. So as you rest tonight, as your thoughts begin to soften and your breathing slows, think about those tiny fluctuations. Think about the quantum ripples that became galaxies. Think about the imperfections that made everything possible. The universe didn't need to be perfect to be beautiful. It just needed to be slightly imperfect, slightly uneven, slightly out of balance. And from that imbalance, everything you've ever known emerged. The stars, the planets, the light, the life. All of it traces back to fluctuations smaller than an atom stretched by inflation, to cosmic scales frozen into the structure of space, waiting billions of years to become what they were always meant to be. Seeds of galaxies, seeds of stars, seeds of worlds, seeds of you. But the fluctuations in the CMB don't just tell us where galaxies came from. They also reveal something deeper, something about the universe's age, its shape, its composition, and its ultimate fate. The patterns encoded in those tiny temperature variations hold the answers to some of the biggest questions we've ever asked. And when we study them carefully, when we measure them with precision, they speak to us, telling us not just where we came from, but where we're going. If you could ask the universe 3 questions, what would they be? How old are you? What shape are you? Where are you going? For most of human history, these questions had no clear answers. They were matters of speculation, philosophy, mythology. But then we found the cosmic microwave background, and suddenly the universe could answer. Not in words, but in patterns, in temperature, in light. The CMB is more than a relic of the past. It's a cosmic encyclopedia, written in the language of physics, waiting to be read. One of the most profound things the CMB tells us is the age of the universe. Before we had precise measurements of the cosmic microwave background, estimates of the universe's age varied wildly. Some scientists thought it might be 10 billion years old. Others suggested 15 or 20 billion. There were even debates about whether the universe had an age at all, whether it might have existed eternally in some form. But when satellites like WMAP and Planck mapped the CMB with extraordinary precision, they gave us an answer so specific it feels almost startling. The universe is 13.8 billion years old, give or take about 20 million years. That margin of error is less than 0.2%. It's one of the most precisely known numbers in all of cosmology, and it comes not from guesswork or extrapolation, but from direct measurements of the oldest light we can observe. How does the CMB reveal the universe's age? The answer lies in the patterns of the temperature fluctuations. The size and spacing of the hot and cold spots in the CMB depend on several factors: how fast the universe was expanding, how dense matter was at the time of recombination, and how long it took for sound waves to travel through the early universe before light was freed. By analyzing these patterns, scientists can work backward, reconstructing the conditions of the early universe and determining exactly when recombination occurred. Since recombination happened 380,000 years after the Big Bang, and we know how long ago that was, we can calculate the total age of the universe. It's like looking at tree rings to determine the age of a tree, except instead of rings, we're reading ripples in ancient light, and instead of years, we're counting billions of them. But the CMB doesn't just tell us when the universe began, it also tells us what shape space itself has. This might sound strange. We're used to thinking of space as a stage where events happen, a flat, unchanging background. But in general relativity, Einstein's theory of gravity space is dynamic. It can curve, it can bend. And the overall geometry of the universe, the shape of space on the largest scales, affects how light travels through it. There are three possibilities. Space could be positively curved like the surface of a sphere, which would mean the universe is finite. And if you traveled far enough in one direction, you'd eventually come back to where you started. Space could be negatively curved like a saddle, which would mean the universe is infinite and expands faster at the edges. Or space could be flat, meaning parallel lines stay parallel forever, and the universe extends infinitely in all directions. For decades, cosmologists debated which of these geometries was correct, and then the CMB settled the question. The key is in the size of the temperature fluctuations. In a flat universe, the hot and cold spots in the CMB have a characteristic angular size determined by the physics of sound waves in the early universe. In a curved universe, those spots would appear either larger or smaller, depending on the curvature. It's like looking at a distant object through a lens. If space is curved, it acts like a lens, distorting the apparent size of things. When scientists measured the CMB with WMAP and Planck, they found that the angular size of the fluctuations matched the predictions for a flat universe almost perfectly. Within the limits of measurement error, the universe is flat. Space on the largest scales is Euclidean. This was a surprise to many cosmologists. Theoretical models had allowed for the possibility of curvature, and some even predicted it. But the data was clear. The universe is flat, or so close to flat, that any curvature is too small to detect. What does it mean for the universe to be flat? It means that the total energy density of the universe is exactly at the critical value, the boundary between a universe that will eventually collapse back on itself and one that will expand forever. It's a kind of cosmic tightrope, a delicate balance. If the density were even slightly higher, gravity would eventually overcome the expansion, pulling everything back together in a big crunch. If the density were even slightly lower, the universe would expand so fast that galaxies could never form. But at the critical density, the universe expands forever, but just barely. The expansion slows over time, asymptotically approaching zero, but never quite stopping. That's the universe we live in, a flat universe, a universe on the edge. But there's more. The CMB doesn't just tell us about the geometry of space. It also reveals what the universe is made of. By studying the patterns in the CMB, scientists can determine the relative amounts of ordinary matter, and dark energy. And the results are humbling. Ordinary matter, the atoms and molecules that make up stars, planets, and people, accounts for only about 5% of the universe's total energy density. Everything we can see, everything we can touch, everything we've ever known is a tiny fraction of what's out there. Dark matter, an invisible substance that interacts only through gravity, makes up about 27%. We can't see it directly, but we know it's there because of its gravitational effects on galaxies and galaxy clusters. And dark energy, the most mysterious component of all, makes up about 68%. Dark energy is a kind of anti-gravity, a force that pushes space apart, driving the accelerated expansion of the universe. We don't know what it is. We don't know where it comes from. but the CMB tells us it exists, and it tells us how much of it there is. Let's pause for a moment and think about what this means. The universe you experience, the matter you're made of, is a minority. Most of the universe is invisible, most of it is unknown. And yet the CMB gives us a way to measure it, to quantify it, to understand its role in shaping the cosmos. The patterns in the temperature fluctuations depend on the balance between matter and energy, between gravity pulling things together and expansion pushing them apart. By analyzing those patterns, scientists can tease apart the contributions of each component, determining not just that dark matter and dark energy exist, but exactly how much of each there is. It's one of the most remarkable achievements in the history of science. We've measured the composition of the entire universe by studying light from when the universe was still an infant. There's a common misconception worth addressing here. Some people hear about dark matter and dark energy and assume they're just fudge factors, convenient inventions to make the equations work. But that's not quite right. Dark matter and dark energy are real in the sense that their effects are observable and measurable. We see dark matter's gravitational influence on the rotation of galaxies, on the bending of light around galaxy clusters, on the large-scale structure of the universe. We see dark energy's effects in the accelerated expansion of space, in the way distant galaxies are moving away from us faster than they should be if only gravity were acting. The CMB provides independent confirmation of these components. It's not just one piece of evidence. It's multiple lines of evidence all pointing to the same conclusion. The universe is mostly made of things we don't yet fully understand. And that's not a failure of science. It's an invitation, a reminder that there's still so much to discover. Now, what about the universe's fate? If the CMB can tell us about the past and the present, can it also tell us about the future? The answer is yes, but with caveats. The fate of the universe depends on the balance between dark energy and matter. If dark energy continues to drive the expansion at an accelerating rate, and current evidence suggests it will, then the universe will keep expanding forever, faster and faster. Galaxies will drift beyond each other's horizons. Stars will exhaust their fuel. Eventually, in trillions upon trillions of years, the universe will enter a state called heat death, where all useful energy has been dissipated, where everything has reached the same cold, uniform temperature, where no work can be done, no complexity can exist. It's a quiet end. Not a dramatic collapse, but a slow fade into darkness. And yet, even in that distant future, the cosmic microwave background will still be there, cooler than ever, fainter than ever, but still glowing, still carrying the memory of the universe's beginning. But there's another possibility, one that current data makes seem unlikely but can't entirely rule out. If dark energy isn't constant, if it changes over time, or if there are other forces we haven't discovered, the universe's fate could be different. It might stop expanding. It might even contract. Some models predict a big crunch where everything collapses back into a hot, dense state, perhaps giving birth to a new universe in a cycle that repeats forever. Other models suggest a big rip, where the expansion accelerates so violently that it tears apart galaxies, stars, planets, atoms, even the fabric of space itself. These scenarios are speculative based on possibilities rather than evidence, but they remind us that the universe is still unfolding. Its story isn't finished. And the CMB, while it gives us profound insights into the past and present, can only hint at what's to come. Let me give you a sense of how precise these measurements are. The WMAP satellite launched in 2001 measured the CMB with such accuracy that it determined the age of the universe to within 1%. That's like measuring the length of a football field to within a centimeter. The Planck satellite launched in 2009 pushed that precision even further, refining our understanding of the universe's composition, its geometry, and its history with unprecedented detail. These satellites didn't just take pictures of the CMB. They analyzed it pixel by pixel, measuring the temperature of millions of points across the sky, looking for patterns, correlations, statistical signatures, that reveal the underlying physics. And from those measurements, they constructed a coherent picture of the universe from its earliest moments to the present day. It's a triumph of observational astronomy, of engineering, of human curiosity. But here's something that often gets overlooked. The CMB isn't static. It's not a fixed snapshot. As the universe continues to expand, the CMB continues to evolve. It's getting colder, its wavelength is stretching, its energy is decreasing. In a billion years, the temperature will have dropped slightly. In a trillion years, it will be even colder, and eventually it will fade to a level so faint that no instrument, no matter how sensitive, could detect it. The universe will have cooled so much that the CMB will be indistinguishable from the vacuum itself. But for now, in this moment of cosmic history, the CMB is bright enough to measure, clear enough to analyze, and rich enough to tell us almost everything we want to know about where we came from, what we're made of, and where we're going. So, tonight as you rest, as your thoughts begin to settle and your breathing slows, think about those measurements. Think about the fact that we can determine the age of the universe to within 20 million years, a precision that would have seemed impossible just a few decades ago. Think about the shape of space flat and infinite stretching forever in all directions. Think about the composition of the cosmos, mostly invisible, mostly unknown, but measurable nonetheless. The CMB is more than light. It's information. It's a message from the early universe written in patterns of temperature waiting for us to decode it. And when we analyze it carefully, it tells us stories we never imagined. Stories about the beginning of time, stories about the fabric of space, stories about the fate of everything. But the CMB holds one more secret one that scientists are still trying to understand. Because when you look at the patterns closely, when you measure them with the utmost precision, you find things that don't quite fit. Anomalies, unexpected features, cold spots, and strange alignments that challenge our understanding. The universe, it seems, still has mysteries to reveal. And some of those mysteries might change everything we think we know. What if the universe is trying to tell us something we're not ready to hear? What if hidden in the oldest light and the patterns we've measured so carefully, there are clues to something stranger, something bigger, something that doesn't fit the story we've been telling ourselves? Sometimes the most important discoveries begin not with answers, but with questions that shouldn't exist, with anomalies that refuse to go away. The cosmic microwave background, as we've seen, is remarkably uniform. Nearly the same temperature everywhere, with only tiny fluctuations marking the seeds of galaxies. The patterns match theoretical predictions with stunning accuracy. It's one of the great triumphs of modern cosmology. And yet, when scientists looked closely when they examined the data with the most sensitive instruments ever built, they found something unexpected, something that doesn't quite fit. Not dramatic contradictions, but subtle oddities. Features that shouldn't be there, or at least features we can't fully explain. Cosmologists, with their characteristic understatement, have given these anomalies names that sound almost whimsical. The cold spot, the axis of evil, the hemispheric asymmetry. But behind these names are genuine mysteries puzzles that challenge our understanding of the universe and hint at the possibility that there's more to the story than we thought. Let's start with the cold spot. In 2004, astronomers analyzing data from the WMAP satellite noticed something strange in the southern hemisphere of the CMB sky, a region roughly 10 degrees across, about 20 times the diameter of the full moon, that was significantly colder than the surrounding areas. Not just a little colder, but colder by about 70 microkelvins, which in the context of the CMB's tiny fluctuations is actually quite substantial. At first, scientists thought it might be a measurement error, a glitch in the instruments, or perhaps contamination from foreground objects like galaxies or dust clouds. But when they checked and rechecked the data, when the Planck satellite later confirmed the finding, the cold spot remained. It was real, and it was puzzling, because according to the standard models of cosmology, a fluctuation that large, that cold, should be extremely rare. Statistical analysis suggested that the probability of such a cold spot appearing by random chance was less than 1%. Not impossible, but unlikely enough to make scientists pause. What could cause the cold spot? Several theories have been proposed, each stranger than the last. One possibility is that it's simply a statistical fluke, a rare fluctuation that happened to occur in the observable universe. After all, if you flip a coin enough times, you'll eventually get a long string of heads. Maybe the cold spot is just cosmic bad luck, nothing more. But that explanation feels unsatisfying. Another possibility is that the cold spot marks the location of a supervoid, an enormous region of space with much less matter than average. As light from the CMB passes through a supervoid, it loses energy which could make it appear colder. In 2015, astronomers did find evidence of a large void in that direction, though it wasn't quite large enough to fully account for the temperature drop. The mystery deepened. And then there are more speculative ideas. Some physicists have suggested that the cold spot could be evidence of a collision between our universe and another universe in a multiverse, a place where two cosmic bubbles touched briefly in the distant past, leaving a scar in the CMB. It's a bold hypothesis, one that stretches the boundaries of testable science. But it's an indication of how seriously cosmologists take this anomaly. When the data doesn't fit, you don't ignore it. You ask what it might mean. Then there's the axis of evil, a name that sounds more ominous than it actually is. In the early 2000s, scientists analyzing the large-scale structure of the CMB noticed something peculiar. The temperature fluctuations, when averaged over very large angular scales, seem to have a preferred direction. Certain patterns in the CMB aligned with each other in ways that seemed too coordinated to be random. It was as if the universe had an axis, a kind of cosmic spine around which the fluctuations were organized. This shouldn't happen. According to the cosmological principle, the idea that the universe is the same in all directions on large scales, there should be no preferred orientation. The CMB should look statistically the same no matter which way you point your telescope. But the data suggested otherwise. The quadrupole and octupole moments of the CMB, technical terms describing specific patterns in the temperature fluctuations, were aligned with each other and seemed to point toward a particular region of the sky. Some scientists jokingly called this alignment the axis of evil, a playful reference to how unexpected and unsettling it was. Is the axis of evil real, or is it another statistical fluke? That's still an open question. Some researchers argue that the alignment could be caused by systematic errors in the data, by the way we process the measurements, or by foreground contamination from our own galaxy. Others point out that when you search for patterns in large data sets, you're bound to find some that look significant just by chance. It's a bit like seeing shapes in clouds. If you look long enough, you'll find a dragon or a face, but that doesn't mean the clouds are trying to tell you something. And yet, the axis of evil persists. Multiple independent analyses have confirmed the alignment. The Planck satellite, with its superior sensitivity, saw it too. And while no one is claiming it proves anything definitive, it remains a puzzle, a reminder that the universe might not be as perfectly isotropic, as perfectly uniform as we assumed. There's also the issue of hemispheric asymmetry, another subtle anomaly that challenges the standard cosmological model. When scientists compared the northern and southern hemispheres of the CMB, they found that the fluctuations in one hemisphere are slightly larger, slightly more pronounced than in the other. The difference is small, only a few percent, but it's statistically significant. Again, this shouldn't happen. If the universe is truly homogeneous and isotropic, if the cosmological principle holds, then both hemispheres should look essentially the same. But they don't. One side of the sky is just a little bit more active, a little bit more varied than the other. It's like looking at a painting and realizing that one half has slightly bolder brushstrokes than the other. The painting is still beautiful, still coherent, but there's an asymmetry you can't quite explain. What do these anomalies mean? Are they telling us something fundamental about the universe, or are they just noise artifacts of measurement? statistical quirks that will disappear with better data? Honestly, we don't know yet. And that uncertainty is both frustrating and thrilling. Science thrives on mysteries like this. They push us to refine our theories, to question our assumptions, to look more carefully at what we think we understand. Some physicists have proposed that these anomalies could be evidence of new physics of processes or structures that existed in the very early universe and left subtle imprints in the CMB. For example, if the universe underwent a phase of anisotropic inflation, a period where it expanded at different rates in different directions, that could explain some of the asymmetries we see. Or if the universe has topology more complex than we assumed, if space wraps around itself in unexpected ways that could create patterns in the CMB that look anomalous but are actually natural consequences of the universe's shape. There's also the possibility, remote but intriguing, that these anomalies are hints of a multiverse. In some versions of inflationary theory, our universe is just one bubble in a vast, eternally inflating cosmos. And if our bubble collided with another bubble at some point in the distant past, it could have left a mark in the CMB. The cold spot in this view might be the scar of such a collision. It's a speculative idea, one that's difficult to test, but it's not entirely outside the realm of scientific inquiry. The CMB has already given us so much information about the universe. Maybe it's also whispering to us about what lies beyond the universe, about the larger structure of reality itself. But let's be careful here. It's easy to get carried away by exciting possibilities, to see significance in every pattern, to assume that every anomaly is a clue to something profound. Science requires skepticism, especially when dealing with data at the edge of our measurement capabilities. Many of the anomalies in the CMB could turn out to be nothing more than statistical noise artifacts of how we analyze the data, or foreground contamination that we haven't fully accounted for. The cold spot might just be a rare fluctuation. The axis of evil might be a coincidence. The hemispheric asymmetry might disappear with better modeling. We have to hold these possibilities lightly without clinging too tightly to any single explanation. The universe doesn't owe us clarity. It doesn't reveal its secrets just because we want it to. Sometimes mysteries remain mysteries for a long time, waiting patiently for the right tools, the right ideas, the right questions. And yet there's value in not dismissing these anomalies too quickly. History is full of examples where scientists ignored data that didn't fit, only to realize later that the anomalies were pointing towards something important. The perihelion precession of Mercury was an anomaly that classical mechanics couldn't explain, and it took Einstein's general relativity to make sense of it. The rotation curves of galaxies were anomalies that didn't match predictions, and they led to the discovery of dark matter. Sometimes the universe speaks in whispers, in subtle deviations from what we expect. And if we're not listening carefully, if we're too quick to dismiss what doesn't fit, we might miss the message. Have you ever felt like something was just slightly off, just a little bit different from what it should be, but you couldn't quite put your finger on that's what these anomalies feel like to cosmologists? The CMB is beautiful. It's consistent. It tells a coherent story about the universe's origin and evolution. And yet, there are these small details, these quiet inconsistencies that suggest the story might be more complicated than we thought. Maybe the universe isn't perfectly symmetric. Maybe the early universe had features we haven't accounted for. Maybe there are forces or structures operating on scales larger than the observable universe influencing what we see in subtle ways. Or maybe we're seeing the first hints of something entirely new, something that will require us to rethink our understanding of cosmology from the ground up. One thing is certain. The anomalies in the CMB have sparked a vigorous debate among scientists. Conferences are held, papers are published, theories are proposed and tested. Some researchers dedicate their entire careers to studying these features, trying to determine whether they're real or illusory, significant or trivial. And that's as it should be. Science progresses not just by confirming what we expect, but by investigating what we don't. The anomalies might turn out to be nothing, but they might also be the key to unlocking the next great breakthrough in our understanding of the cosmos. And we won't know unless we keep looking, keep questioning, keep probing the data for answers. So, tonight as you rest, as your thoughts begin to drift and the world grows quieter, think about those anomalies. Think about the cold spot, colder than it should be sitting there in the southern sky, like a question mark. Think about the axis of evil, a strange alignment that hints at hidden order. Think about the hemispheric asymmetry, one side of the universe just slightly different from the other. These aren't just curiosities, they're reminders that the universe is full of surprises. That even when we think we figured something out, even when the data matches our models almost perfectly, there are always edges, always details that don't quite fit. And those details, those anomalies, those shadows in the cosmic microwave background, they might be the most important things of all, because they're telling us that there's more to discover, more to understand, more mysteries waiting in the oldest light. But before we reach the end of this journey, before we rest in the quiet knowledge of what the CMB has taught us, there's one more thought to hold. Because the cosmic microwave background isn't just about the past. It's not just a snapshot of the universe when it was young. It's something more enduring, more patient, more eternal than that. The CMB will outlast almost everything. And in that longevity, in that refusal to fade completely, there's a kind of comfort, a kind of promise, that even as everything changes, even as stars die and galaxies drift apart, the universe will remember where it came from. And that memory written in light will remain. There's a kind of light that will never die, not in the way we usually think of death, not suddenly, not dramatically, but it will fade so slowly, so gently, that even after all the stars have burned out, even after the last galaxy has drifted beyond the edge of what we can see, this light will still be there, fainter than a whisper, colder than the darkest night, but present, always present. The cosmic microwave background is the most patient storyteller the universe has ever known. And its story isn't over yet. Let's think about the future for a moment. Not the near future, not thousands or millions of years from now, but the deep future, the far future, the kind of time scales that make human history feel like the blink of an eye. In about 5 billion years, our sun will exhaust its hydrogen fuel and begin to die, swelling into a red giant, possibly consuming Earth in the process. In 10 billion years, most of the stars in the Milky Way will have used up their fuel. New stars will still form for a while, but the rate of star formation will slow dramatically as the universe runs out of the raw materials needed to make them. In 100 billion years, the accelerated expansion of space driven by dark energy will have carried most galaxies beyond our cosmic horizon. If there are civilizations in those distant galaxies, they'll look out at the night sky and see nothing but darkness, no other galaxies visible, no way to know that a larger universe once existed. They'll think they're alone. And, in a sense, they will be. But through all of this, the cosmic microwave background will persist. It will continue to cool, degree by degree, as the universe expands. Right now, it's at 2.725 Kelvin. In a trillion years, it will be colder, perhaps around 0.3 Kelvin. In 100 trillion years, colder still. The wavelength will stretch further and further into the radio spectrum. The energy will drop lower and lower, but the light will still exist. Photons that were freed during recombination nearly 14 billion years ago will still be traveling through space, still carrying the memory of the universe's beginning. And here's what's remarkable. Those photons will outlive almost everything. They'll outlive stars. They'll outlive black holes, which will eventually evaporate through Hawking radiation, over time scales so long they're almost incomprehensible. The CMB will be one of the last remnants of the hot, dense state from which the universe emerged, a fading echo, a memory that refuses to be forgotten. Does that thought comfort you, or does it feel lonely? There's something profound about the idea that the universe will never completely let go of its past. That even in the far future, in an era so distant that no stars shine, no galaxies exist, no complexity remains, the CMB will still be there glowing faintly in the void. It's as if the universe is saying, I remember. I remember where I came from. I remember when I was young and full of light, and I will carry that memory forward no matter how cold I become, no matter how empty. Some scientists find this beautiful, others find it melancholic. Perhaps it's both. A testament to endurance. A reminder that even in the face of entropy, even as everything fades, something persists. But let's return to the present, to this moment, to this epic in cosmic history, where stars still shine and galaxies still spiral, and the CMB is still warm enough, still bright enough to be measured and studied. What have we learned from this ancient light? What has it taught us about ourselves, about our place in the universe, about the nature of reality itself? The cosmic microwave background has given us more than data. It's given us perspective. It's shown us that we're part of a story far larger and far older than we ever imagined. That the atoms in our bodies were forged in stars that formed from density fluctuations in the early universe. That those fluctuations in turn originated from quantum ripples stretched to cosmic scales by inflation. That everything we are, everything we know, traces back to processes that happened in the first fraction of a second after the Big Bang. The CMB has also taught us humility. Before we discovered it, we thought we understood the universe reasonably well. We knew about stars and galaxies, about gravity and light. But the CMB revealed that most of the universe is invisible. That dark matter and dark energy dominate the cosmos, and we still don't fully understand what they are. It showed us that the universe had a beginning, a moment when time itself started, and that we can study that moment not through speculation, but through observation. It gave us the tools to measure the age of the universe, the shape of space, the composition of everything. And in doing so, it reminded us how much we didn't know, how much we still don't know. The universe is vast, and we're only beginning to read its story. There's a lesson in that, isn't there? The idea that knowledge doesn't close doors, it opens them. Every answer the CMB has given us has led to new questions. What caused inflation? What is dark matter made of? What is dark energy? Why are there anomalies in the CMB that don't quite fit our models? Are we living in a multiverse? These aren't questions we could have asked before we discovered the cosmic microwave background. They emerge from the data, from the patterns, from the subtle details hidden in the oldest light. And they'll keep us busy for generations, maybe centuries, maybe longer. Science doesn't end when we figure something out. It begins again with deeper questions, with more refined tools, with a clearer understanding of what we don't yet understand. And here's something worth holding for a moment. The cosmic microwave background connects us to the universe in a tangible way. It's not abstract. It's not theoretical. It's real physical light passing through your body right now. Every second, billions of CMB photons stream through the room where you're resting, through your skin, through your bones, carrying with them the memory of the moment when atoms first formed and light was set free. You are bathed in the echo of creation. You always have been. You always will be. It's a connection that transcends time, that links you to the earliest moments of cosmic history. And there's something deeply moving about that. The universe isn't something distant and unreachable. It's here, touching you, holding you, reminding you that you're part of something ancient, something vast, something that began long before you were born and will continue long after you're gone. But perhaps the most important thing the CMB has taught us is patience. The universe doesn't hurry. It took 380,000 years for light to be freed. It took billions of years for galaxies to form. It took even longer for stars to create the heavy elements needed for planets and life. And it will take trillions of years for the universe to cool to the point where the CMB is barely detectable. Everything happens on time scales so long, they're almost beyond comprehension. And yet, we with our brief lives, our fleeting moments of consciousness, have found a way to measure it, to understand it, to appreciate it. We have looked at light from the dawn of time and read its message. We've decoded the patterns, calculated the numbers, reconstructed the history. And we've done it not through magic or guesswork, but through careful observation, through mathematics, through the patient accumulation of knowledge over generations. That's an achievement worth celebrating, not because it makes us special, but because it shows what's possible when we pay attention, when we ask questions, when we refuse to accept that the universe is unknowable. So, as we come to the end of this quiet journey, as your breathing slows and sleep begins to pull you gently under, let's hold one final thought. The cosmic microwave background is the oldest light in existence. It has traveled for nearly 14 billion years to reach you. It has seen the birth of the first stars, the formation of the first galaxies, the slow dance of matter as it clumped and clustered into the structures we see today. It has witnessed the sun ignite Earth, cool life begin. It has been there for every moment of cosmic history, quietly glowing, patiently waiting, carrying the memory of the universe's infancy through the vast expanse of time. And tonight, right now, it's touching you, not metaphorically, literally. The oldest light in existence is passing through your body, connecting you to the moment when everything began. There's comfort in that connection, a kind of peace, because it means you're not separate from the universe. You're part of it, made from it, held by it. The same forces that shaped galaxies shaped you. The same light that filled the early universe still surrounds you. The same story that began 13.8 billion years ago includes you here in this moment, listening to these words, breathing softly in the dark. You are the universe experiencing itself, a brief flicker of consciousness in the long, slow unfolding of cosmic time, and that's enough. That's more than enough. It's everything. The CMB will outlive stars. It will outlive galaxies. It will outlive almost everything. But you're here now, in this epoch, in this moment when the universe is still young enough to remember, still warm enough to glow, still full of light and possibility. And you get to witness it. You get to know it. You get to rest under the gentle touch of the oldest light, feeling it brush against you like a memory from the beginning of time. That's a gift. A quiet, beautiful gift. And maybe that's what the universe has been trying to tell us all along, that we're connected, that we're remembered, that we're part of something so much larger than ourselves, and yet we're held gently within it always. Thank you for drifting with me tonight through the cosmic microwave background, through the light that remembers everything. Thank you for listening, for wondering, for letting your curiosity carry you across the vast expanse of time. The universe has so many more stories to tell, so many more quiet wonders to explore, and I'll be here ready to share them with you whenever you're ready to rest and listen again. Until then, sleep well, dream gently, and remember, the oldest light is still with you, still glowing softly in the dark, still carrying the memory of when everything began. Good night.